Welcome, and thank you for joining us. My name is Joe Stoller. I am a senior research and development chemist at Epic Resins in Palmyra, Wisconsin. Today, we will discuss the versatility of polyurethanes for power electronics. These polymers can be modified and tailored to suit a multitude of demanding properties required in many different electric applications. To start, I will share a little about Epic Resins. Epic is a formulator of high-performance epoxy and polyurethane thermoset polymer solutions. We have been developing and manufacturing polymer solutions across many industries for over 65 years. Our R&D lab and manufacturing is in Palmyra, Wisconsin, conveniently located between Chicago and Milwaukee. We manufacture over 3,000 products and service 1,500 domestic and international customers from this location. Epic Resins is ISO 9001 and 14001 certified, as well as OSHA Sharp certified. When working with Epic Resins, our customers gain access to our technical sales team, as well as our research and development chemists. Access to our development chemists and lab capabilities acts as an extension to your design team. This level of project support helps you achieve results in condensed time frames to shorten your time to market. Automotive electronics encompass a vast range of applications. Urethane polymers touch the flow of electrical power throughout the automotive system, starting with the on or off-board chargers, flowing to the battery, followed by the inverter to the ECM, then to the powertrain. The efficient and reliable flow of energy is essential. Each of these demanding applications needs polymers to function reliably. Peripheral control systems like sensors and light fixtures also depend on urethane technology. Whether you need a polymer with high TG and thermal resistance for a motor application, or a soft polymer with great adhesion and water resistance to protect an external sensor, the versatility of urethanes can attain and exceed these demanding properties. Urethane polymers are utilized in potting and encapsulation for all of these applications. The primary purpose of these materials is to protect sensitive electronics from their surrounding environments so that they can function efficiently and reliably. The terms potting and encapsulation are sometimes used interchangeably. However, potting refers to a process where the shell or pot filled with resin becomes a part of the finished component, and encapsulation refers to when the component and cured polymer are removed from the pot to be placed in an assembly. This is an example of a potted part, and this is an example of encapsulation. Some important criteria for automotive electronics include thermal management, flame suppression, structural assembly, improved reliability and product life, and protection from harsh environments. I will explain how urethane polymers have the versatility to satisfy this list of demanding criteria. To understand the versatility of polyurethanes, you must first understand its chemistry. We formulate polyurethanes from a molecular structure to property relationship. Ultimately, we utilize our vast knowledge of molecular building blocks to impart properties needed for your final polymer. From processing requirements for viscosity and gel time, to physical properties of tensile strength, elongation, glass transition temperature, dielectric strength, and thermal conductivity, all of these properties can be adjusted to satisfy specific requirements. I will expound on each of these properties along with the formulation involved for urethanes to have this versatility. We will begin with gel time. Gel time is generally defined as the time required for the reaction of the polymer to proceed to a point where the polymer has more elastic properties than fluid properties. More specifically, when a two-component material is mixed, the viscous properties dominate. As a polymer begins to react, it displays more viscoelastic properties in a dynamic nature until the polymer chain gets long enough that the elastic nature is more prominent than the viscous nature. The process for each application will have a specific demand for gel time or throughput requirements. Urethane polymers can have very fast reactivities to just a few minutes to as slow as several hours. This versatility gives your process engineering team latitude to fine-tune their process. Urethane chemistry has more reaction versatility than most polymer types. This versatility is rooted in two unique properties: the molecular structure of the monomers and the catalyst mode of action and activity. The building block molecules that can be utilized in the production of polyurethanes have different reactivities. These reactivities are dictated by their molecular structure. The position of the reactive group will change how fast it reacts. For example, this is an NCO group on an MDI, and this has a 4-position NCO group on this side, has a 2-position NCO group on this side. The 4-position is much faster. If you formulate with MDI with more 4-position NCO, you will have a faster reacting polymer. This allows us to utilize the appropriate molecular structure when tailoring the reactivity of a polyurethane. Catalysts can also be used to craft the specific reactivity that an application needs. There are catalysts utilized for slow and consistent polymerization for delicate applications requiring gradual reactivity. In contrast, some applications require very rapid polymerization for high throughput applications, as seen in this demonstration. When we combine our knowledge of molecular structure reactivity with the nuances of catalyst types, the gel time possibilities of polyurethanes are essentially endless. Once the polymer is gelled and completely cured, we turn our attention to the cured properties of the polymer. Glass transition temperature, or TG, is an important thermal property with great versatility in urethanes. TG is the temperature where a material transitions from a hard and rigid glass-type material to a soft, pliable material, as shown with the vertical blue strip on this graphic. Each application within power electronics has varying operating temperature ranges, resulting in different optimum TGs. Typically, applications with sensitive components and vibrational conditions will find greater longevity with a low TG product. For example, motor controllers or battery management systems contain sensitive electronics that can be damaged from thermal cycling in under-the-hood environments. Utilizing a soft, low TG urethane elastomer will protect these components from these thermal and vibrational stresses. Alternatively, motor applications that run at high temperatures for prolonged periods need a material with high thermal stability, requiring a high TG. A high TG polymer gives greater molecular stability and polymer longevity, protecting motor conductors from harsh environmental conditions. The TG of a system is primarily influenced by the molecular linkages and frequency of these linkages. These linkages are classified by 3 different architectural features of the molecular building blocks: the backbone structure of the monomer, the molecular weight of the monomer, and the functionality of the molecular structure. All 3 of these architectural features come together to influence the cross-link density and hence the TG. These features influence the TG because as the polymer heats up, the linkages begin to flex, stretch, and move. The density and type of these linkages dictate the temperature at which this occurs. Therefore, by manipulating the backbone structure, the molecular weight and functionality of that structure, we manipulate the TG to fit the desired application specifications. This animation demonstrates how 2 polymers can have different cross-link densities and hence TGs. Another critical property of your polymer is physical strength. Physical strength is a measure of a polymer's ability to withstand deformation. There are a myriad of methods to evaluate physical strength, but the most common is to evaluate elongation and tensile strength of the cured polymer. These 2 methods give us a good snapshot of how a material behaves under stresses, allowing us to get a clear comparison to other polymer systems. As you can see in this chart, polyurethanes have a large range of tensile strength and elongation. For example, Urethanes can have soft, gel-like properties similar to a silicone, or be formulated to be hard and rigid like nylon or polycarbonate. You notice each time we look at how to modify a urethane property, we look at its chemistry. Similar to how we modify the TG, we again look at the same molecular building blocks: the backbone structure of the monomer, the molecular weight of the monomer, and the functionality of the molecular structure. When looking at the tensile strength and elongation, we put a little more emphasis on the backbone structure linkages. These backbone structure linkages and their frequency are great tools to modify the strength of the polymer. I like to use the analogy that these backbone structures are a little bit like springs of the polymer. The type of linkage in the backbone combined with the cross-link density will result in different tensile and elongation properties. For example, I have two different springs in my hand, a rigid spring and a flexible spring. The rigid spring is like the conjugated hexane ring in a molecular backbone, which tend to be more rigid. This flexible spring is more like the polyethylene glycol linkages of a hydrocarbon, which are more flexible. If you have more conjugated hexane rings in the backbone, it will be more rigid. If you have more polyethylene glycol linkages, you will have more flexibility. By knowing how these molecular structures affect the strength of the polymer, you can then understand how to formulate the polymer with strength like polycarbonate or a softer polymer similar to silicone. Thermal management is critical for most electrical applications, making thermal conduction crucial. Thermal conductivity is the measure of a material's ability to conduct heat. This infrared video gives you a visual representation of three polymers with different thermal conductivity. These three products are EPIC 7524, RM 2018, and S7527. S7524 on the bottom left has low thermal conductivity. RM 2018 on the bottom right has medium thermal conductivity. S7527 on the top has high thermal conductivity. The infrared image shows as the pucks are heated from the bottom, you can see that the S7527 gets hot faster than the other two, indicated by the yellow color. Obviously, this shows it is pulling heat from the hot plate faster than the S7524 and the RM 2018. Applications that process electrical energy can produce large amounts of heat. Dissipating this heat is vital to performance and longevity. Polyurethanes have great versatility to provide thermal conductivity for potting and encapsulation applications. Choosing the correct thermal potting compound for your power electronics will improve efficiency and lifespan due to reduced thermal cycling from better heat transfer. This graph compares the thermal conductivity range of common materials. Polyurethane systems can have thermal conductivity from 0.2 to 4 watt per meter Kelvin, with the same range as silicone materials and much higher than acrylic or nylon. Polyurethanes can be formulated to provide the thermal transfer required for some of the most demanding applications in power electronics. Refining the particle kinetics of the potting compound is key to improving its thermal conductivity. The thermal conductivity of a polymer is primarily dictated by the type, size, and loading of a thermally conductive mineral filler in the polymer. When formulating for thermal conductivity, the first decision revolves around filler type. Different mineral fillers have varying thermal conductivity as well as other properties that are imparted into the polymer. For example, aluminum oxide has excellent thermal conductivity and is very hard. Aluminum trihydrate is lower in thermal conductivity and not as hard, but has flame suppression properties. Once the mineral is chosen, the thermal conductivity can be further optimized based on the level of loading and the size of the particles used. To illustrate this, I have three different sets of marbles. This first picture shows a lot of large marbles with lots of interstitial space. This second picture shows smaller marbles, but still a significant amount of interstitial space. This last group of marbles is a mixture of many sizes. You can see much better contact of the marbles. The marble example demonstrates how particle size distribution helps optimize particle contact and loading to improve overall particle kinetics and thermal conductivity. Next, we look at the viscosity of a polyurethane system. Viscosity is the measure of the force of deformation or resistance to the flow of a liquid. For comparison, this graph shows the viscosities of everyday materials compared to polyurethane systems, which range from 200 to 10,000 centipoise. For potting and encapsulation, the flow of the urethane is essential to protecting sensitive components from a myriad of environments. Without proper flow, these components will not be sufficiently coated and thus not protected. This video is a great example of flow in and around sensitive components. You see the potting compound being injected under the PCB. This produces complete underflow of the board in addition to flowing up the vent holes and completely around the board components. When developing a manufacturing process, viscosity data is vital to achieve complete encapsulation of components. Many factors affect how a urethane potting compound flow in an application. The primary factors include monomer molecular weight and its functional groups, the level and type of filler loading, and the use of wetting agents. In most cases, the cured properties will primarily dictate the monomers used, so viscosity typically must be adjusted through the modification of fillers and wetting agents. When mineral fillers are used in a system, their particle size has a significant effect on the viscosity of the system. Ultimately, with smaller sized particles, there is a greater surface area to interact with the resin monomer. This increases the viscosity. As the particle size of a filler increases, the surface area is lower, which in turn reduces the viscosity. This graph shows how particle size affects viscosity. The material with a smaller particle size filler has a higher viscosity, and the opposite is true for the large particle size with a lower viscosity. Wetting agents are another tool that can help to reduce the viscosity of systems with high filler loading and/or small particles. Wetting agents work by interacting with the filler particles in place of the resin, changing the viscous interaction and reducing viscosity. For example, this video shows two identical polyurethane systems with and without wetting agent. The material on the left contains a wetting agent and flows much better than the material on the right, which does not contain any wetting agent. When adjusting the viscosity of a system, these tools allow for vast adjustment to reach an application's requirements. The last property we will discuss is dielectric strength. Power electronics are evolving into sophisticated systems with intricate electronic components and high voltage systems in smaller and smaller packages. Ensuring that these components remain isolated from each other in these condensed architectures is essential to preventing electrical failures, fires, and potential hazards. This is where polyurethane potting materials with high dielectric strength come into play. When an electric field surpasses a material's dielectric strength, it undergoes dielectric breakdown. This breakdown can lead to electrical arcing, short circuits, and damage to surrounding components. For EV electronics, safety and reliability are paramount. Minimizing the risk of dielectric breakdown is a primary concern. Urethane insulating materials are essential to EV electronics to prevent dielectric breakdown due to their inherent high dielectric strength. Selecting the right material with the appropriate properties is crucial. To improve dielectric strength, you need to understand the mode of failure in dielectric breakdown. The factors that influence dielectric breakdown of a polymer include polymer type, filler type and loading, as well as any additives present. Dielectric breakdown occurs when the molecular stability of an insulating material allows electrons a free path to travel. Ultimately, this is about stability of electrons in the material. This is an illustration of dielectric breakdown. As a voltage is applied, electrons build up on the surface of the electrode. If there is a path of unstable electrons, the charge will travel through the polymer as shown. The more stable the electrons are, the more difficult it is to make them move through the material. We formulate polyurethanes that have molecular structures, fillers, and additives with very stable electron shells. When formulated this way, it significantly impedes the flow of electrons and increases dielectric strength. With the wide range of important criteria in automotive electronics, a versatile polymer is essential to satisfy these needs. Whether you need flexibility to improve your manufacturing process, or you are fine-tuning your component design to take reliability to the next level, or any combination, polyurethane chemistry can be modified to help achieve those goals. At Epic Resins, we are industry leaders in formulating innovative urethane polymers. Our R&D chemists continuously develop new materials with novel molecular structures to withstand the unique and extreme demands of EV power electronics, battery systems, sensors, and lighting. These urethane polymers have the versatility needed for your electronics application.